All right, welcome to episode 15, and in this episode we're going to talk quite a bit about 6809 assembly language programming. We're going to develop a ROM monitor and show what it can do. And as always, the updated schematics and code are on GitHub, and you can find a link in the video description. One important thing to note is that there are important fixes to the portion of the schematic that interface the 6850 ACIA chip and the FT232RL breakout, and essentially serial communications is not going to work correctly unless you build the updated version of the schematic, so do please make a note of that. Okay, let's get started. Let's start our discussion of 6809 assembly language by reviewing the 6809 registers. It's essential to understand the 6809 registers because most instructions operate on registers. The 6809 has two 8-bit accumulators called A and B. They are used as source and destination for ALU operations and can also be used for temporary values and for passing argument values to subroutines and returning values from subroutines. The D register is a 16-bit view of A and B, where A is the most significant byte and B is the least significant byte. It is used for instructions with a 16-bit operand or result. The X and Y registers are 16-bit index registers. They are typically used as pointers to memory locations and allow quick access to variables and array elements in memory, but can also be used for other purposes. The S register is the 16-bit main stack pointer register. It determines where in memory values are pushed onto and popped off of the main stack. The stack is used to store return addresses for subroutine calls and returns, and is also very useful as a way to store register values temporarily, and also to allocate small memory buffers needed by subroutine calls. The U register is the 16-bit user stack pointer. The user stack is independent of the main stack. We probably won't be using the user stack in our monitor program, but it can be useful for applications with multiple stacks, such as programming language interpreters. The DP register stores the upper 8 bits of direct page addresses and determines which 256-byte chunk of memory is used for direct memory references. We'll talk more about direct addressing when we discuss addressing modes. There are two registers that aren't usually accessed directly, but are nonetheless very important for understanding 6809 code. The PC register is the 16-bit program counter. It stores the address of the next instruction to be fetched from memory. Jumps, conditional jumps, subroutine calls, and subroutine returns all change the value of the program counter in order to affect which instruction in the program is executed next. Although the program counter is generally not referred to directly, the 6809 does support PC relative addressing, although we won't be using that in the monitor program. CC is the 8-bit condition code register. It stores flag bits produced by ALU operations, such as whether a carry was generated. It also contains the mask bits that allow normal hardware interrupts and fast hardware interrupts to be enabled or disabled. Next, let's discuss the 6809's addressing modes. The addressing mode used by an instruction determines how it accesses its operands. The types of operands are registers, memory locations, and immediate values. In the inherent addressing mode, the instruction opcode completely specifies its operand. As an example, the INC-A instruction increments the value in the A register by 1. In the immediate addressing mode, the instruction uses an immediate 8-bit constant value that is loaded from the encoded instruction. In the example, the LDA instruction loads the immediate value hex C8 into the A register. Note that immediate values must be prefixed with a hash symbol. In the example, the $sign indicates that the constant is hexadecimal. In the extended addressing mode, the instruction uses a 16-bit address loaded from the encoded instruction. This address specifies a memory location. In the example, the value of the A register is stored to the 1-byte memory location at address hex 8000. In the extended indirect addressing mode, a 16-bit address encoded in the instruction specifies a 2-byte memory location from which an address is loaded, and then the loaded address is used as the referenced memory location. In the example, a 2-byte address is loaded from memory locations hex 1000 and hex 1001, and the contents of the A register are then stored at the 1-byte location specified by the loaded address. The direct addressing mode is like the extended addressing mode, except that only the low 8 bits of the referenced address are encoded in the instruction. The high 8 bits of the referenced address come from the DP register. In the example, an address is formed from the contents of DP, which is the high byte of the address, and hex 13, which is the low byte of the address. A single byte is loaded into the A register from this address. The register addressing mode allows an instruction to access an arbitrary combination of registers. In the example, the push S instruction pushes the B and A registers onto the main stack. First, the address in the S register is decremented, and the value of the B register is stored at the decremented address. Then the S register is decremented again, and the value of the A register is stored. The indexed addressing mode allows the address of a memory operand to be specified as an offset from a base address in the X, Y, S, or U registers. In the first example, the Y register is used as the base address, and a single byte is loaded from that address into the A register. In this case, the offset is implicitly 0. In the second example, an address is computed by adding the value of the B register to the base address in the Y register, and a byte is loaded from this address into the A register. In the third example, an address is computed by adding the constant value -3 to the base address in the Y register and loading a byte from the resulting address into the A register. The indexed addressing mode is very useful for accessing variables and array elements relative to a base address in a pointer register. Amazingly, there are even more modes and variations, including indexed indirect, auto increment and decrement, and PC relative. You can read the 6809 datasheet for more details. Alright, so how do we actually write 6809 assembly language programs? So I think the most important thing to keep in mind is that assembly language programming is just programming. All the good practices and techniques that you know from programming in other programming languages really do apply at the assembly language level. But there are some specific things that I think are helpful to use. One thing that I think is really nice is to have a book. I'm old enough that I actually like to read books about things, and so this was a book that I ordered from Amazon, Amazon Marketplace for the 6809. I think I just paid a few dollars for it. I read this thing more or less cover to cover, and it was actually quite good. So you might get this book, maybe get another one. Really, really helpful, I think. It's definitely useful to read other people's code just to get a sense of what programs look like for the language that you're using. Certainly you will want to have an online instruction set reference, and I will link to the one that I've been using in the video description. Because this is hardware programming, we're going to be programming hardware devices. You will definitely want to have data sheets for all of the hardware devices that are in your system. And most importantly, I think when you're debugging firmware for any kind of embedded system, you need to have some way of making program state visible when you are debugging, tracking down problems. Once you have your UART integrated in your system and it works, that's really excellent because it means you can basically have debug print statements that send information back to your terminal program, and that's really useful for debugging. So here is what I would like the ROM monitor to be able to do. So when the ROM monitor starts, it should initialize all of the hardware devices that are present in the system, and then enter a command loop where repeatedly it waits to receive a command from the user and then carries out that command. I would like the command loop to be extensible so it is easy to modify the monitor program to add support for new commands. One important type of command that should be supported is the ability to do arbitrary inspections of memory locations and modifications of memory locations, so we have complete control over the memory in the system. As a special case of that, I'd like to be able to load arbitrary code and data into RAM in Intel hex format. And specifically what I'd like to be able to do is assemble programs, convert them into Intel hex format, and then have the ROM monitor load the user program into RAM. So here is the memory map of the system. Low 32K is RAM, then there's 4K of I/O space, and then the remainder of the address space is ROM. So the ROM monitor obviously is loaded into this ROM section. If we sort of expand the RAM section of the memory map, here's kind of what it will look like roughly. In the low addresses will be global variables variables used by the monitor program, and then at the high addresses in RAM, we'll have a stack that, of course, grows downwards in memory towards lower addresses, and then the gap in between these global variables in the stack we can use for arbitrary user code and data. So when I write a little test assembly program, I can basically specify that it is going to use addresses sort of above the variables but below the stack. And basically, we should be able to load arbitrary code into this area and execute it. So a couple of stretch goals would be the ability to assemble code into memory and disassemble code from memory. I am not planning to write an assembler or disassembler, but if I happen to find one that's easy to include, I might include it.
Many hours later.
Okay, so I wrote a simple ROM monitor program. It supports the following commands. The E command echoes some text back to the terminal. That's just for testing. The question mark command prints an identification string. That's also for testing. The A command sets the current monitor address, and the R and W commands read bytes from memory or write bytes to memories at the current address. The D command downloads Intel hex data into memory at whatever address is specified by the hex data. The X command executes code at the monitor's current address, and the S command calls a subroutine at the monitor's current address. The syntax for monitor commands is the command character, one of these, followed by a space, and then optional data if the command takes arguments. So here are some examples. If we say A space 1000, that means set the current monitor address to hex 1000. If we say R space 10, that means read 16 bytes, hex 10 is 16, read 16 bytes from memory at the current address, and then print out the hexadecimal representation of those bytes. If we say W dead beef, that means write 4 bytes of data with these hex values to memory at the current address. And both the R command and the W command change the current monitor address by the number of bytes that are either read or written. The D command prepares the monitor to download data into memory in Intel hex format. All right, let's take a quick tour of the code, and I'm not going to go into a lot of detail, but I will show the general organization. So up here at the top, we have constant values that are used in the code. Here are the global variables that are used by the ROM monitor, and the important ones are a buffer for the command, the length of the command that is currently in the command buffer, and then the current monitor address. Okay, so now let's quickly look at the code. Here's the entry point, and basically the code sets up a stack, does hardware initialization, sets the initial monitor address to 0, and then goes into the main loop. And the main loop consists of repeatedly printing a prompt, reading a command, and then executing the command again and again. Following the entry point in the main loop, there is a section that contains all of the subroutines used in the monitor program. I'm not going to show all of them, obviously, but one thing I would like to point out is that there's a section that contains just the subroutines that handle monitor commands. So the idea is that each monitor command has a dedicated subroutine that carries out that command. Next, let's look at the constant data, and this is down at the bottom of the source file, and this is basically, mostly it's a bunch of read-only strings. One really important part of the constant data is these two variables here, monitor commands and monitor dispatch table. And so the idea is that monitor commands is simply a null-terminated character string containing the command characters. And that way, if we want to add a new command, we just have to add a new value to this string. And then the monitor dispatch table is, for each of these command characters, the address of the subroutine that handles that command. So it's quite easy to add new commands to the monitor. You just add the command character here, and then you add the corresponding subroutine address to this table, and that's all you have to do. Before we show a demo of the monitor program in action, let's talk about our test program. So what the test program does is it has its entry point at hex 1000, which is in RAM. It repeatedly, starting from 0, outputs the value of a counter variable to port 8000 hex, which is port A of the 82C55A, and then increments the counter and then does a delay and just does that over and over again. So if this program is executing, essentially what we should see is steadily increasing counts output to port A of the 82C55A. And so the idea is that we are going to assemble this into Intel hex format. And what you will see when I do the demo is I'm going to download this Intel hex file into the 6809 system. So this is what Intel hex format looks like. It's basically just a textual representation of binary data, and it's simple enough that it can be parsed relatively easily from assembly language programs like our ROM monitor. Okay, let's see the monitor program in action. All right, so let's start the demo. So here I am in QtCom, which is the serial terminal that I'm using. So I'm going to reset the device. So it prints the all your base or belong to us message just as a way of letting us know that the system is on. This is the ROM monitor prompt. It shows the current monitor address, which is by default 0. Okay, so let's try a few commands. So we'll start out with the question mark command, and that just has the ROM monitor printout, just a simple identification string. The E command basically will have the ROM monitor echo some text that we specify back. So here it did print hello world, so that's good. The A command changes the current address, so I'm going to change to address hex 9000. You'll notice that the address changes in the prompt. So let's now read 16 bytes from address 9000 hex, and that is the entry point address. So if we read 16 bytes from that address, this is actually the code that is at the entry point of our ROM. All right, so now I'm going to change the address to hex 1000, and let's actually write some data. So I'll say write the W command dead beef, which is just 4 byte values. Okay, and you'll notice that when we do reads and writes, the monitor address changes by the number of bytes read or written. So I'm going to go back to address hex 1000, and now let's again read 16 bytes. And as you can see, it says dead beef, and it did correctly write those 4 bytes. Now we'll do the more exciting part of the demo, and we're going to use the D command to upload our test program. So I issue the D command. At this point, the ROM monitor is waiting for data in Intel hex format, so I'm going to choose testprog.ihx. So now the terminal program is sending the hex records to the ROM monitor. One thing I will note is I had to change this char delay parameter to 3 milliseconds. It was originally 1 millisecond. We can't have the terminal program sending the data too fast. There's no flow control on the serial connection, but it does look like the upload was complete. The first instruction in our test program is at address hex 1000. So we'll set the ROM monitor address to that address. And now if I execute the X command, that's just going to jump to that instruction. And we won't see anything on the ROM monitor, but we should see the hex display connected to port A on the 82C55A count up. So, all right, I'm executing the program. Let's see if it's working. Okay, so as you can see, the counts on the hex display are counting up, so that means our test program is running. That means that the ROM monitor now can successfully download programs from the host PC into the static RAM, and so now we can write programs and test code without having to actually take the ROM out, so that is very nice progress. All right, so just to wrap up, the ROM monitor works, and it allows us to download programs from the host PC onto the 6809 system, so that is really good progress. I did not implement the built-in assembler or disassembler maybe sometime in the future, but it's not really a big deal. I will note again that there are important fixes to the schematic involving the serial communication, so definitely look at the updated schematic. I didn't make it part of the video, but there was some fairly painful debugging while I figured out what was wrong, but fortunately things are working now. So in future videos, you can expect to see support for interrupts and a keyboard controller. So I will see you in the next video.